We want to continue looking at the content from chapter 12, but before we get into that, I wanted to explain a few things that will provide a framework to give us some very useful ideas, because context is very important when we want to try to understand these things. And so we're going to take a break for a minute from talking about some of these chemistry facts and talk about light, specifically how light is generated. And essentially, there's two very different ways in nature that light is generated. So, what are the mechanisms by which light is generated? There are actually two. The first is by accelerating charges. So I have something that's got an excess of charge on it. I might have some electrons or some protons. It doesn't matter what it is that's charged, but I've got something that's charged. And I accelerate it. I speed it up, I slow it down. A general way that we think about it is, imagine you have an electron and you're shaking it back and forth. So I'm accelerating it vigorously by shaking it back and forth. And as I do that, that electron, which is being accelerated by being shook back and forth, is going to emit light. Now, how is that possible? Well, it takes energy. You have to apply energy to the electron to make it move back and forth. And so the energy that you're putting into making it go back and forth actually gets transformed into light. And that is one way that light is generated. The other way that light is generated is through something that's called an electronic transition. And electronic transitions only happen inside atoms. So you can think of just having some extra charges and you're shaking them back and forth. That's one way that you can generate light. But another way that you can generate light is to have an atom and have the electrons actually transition from one orbital shell into the next orbital shell. And the second one, electronic transitions, that's going to be what we really need to talk about to understand what the remaining material is in chapter 12. But I want to talk a little bit about this first method, accelerating charges, because it gives you a very different quality of light. And so I want to talk about that because then I think the second method will make even more sense. So we want to consider that first method of making light, having a bunch of charges and shaking them back and forth. Now consider having a bar of iron that you stick in a fire. It could be like a poker in a fireplace or whatever. You have a piece of metal like iron and you're heating it up. If you heat it up hot enough, it'll actually start to glow. In other words, if you get it hot enough, it'll start to emit visible light. So what's happening? Well, the iron is made up of atoms which contain charges, electrons and protons, and as you heat it up, those atoms with those charges start vibrating back and forth, faster and faster and faster. The hotter you make it, the faster they vibrate back and forth. And eventually, if you heat it up enough, those charges are vibrating back and forth fast enough to emit visible light. And as you go through this process, there are actually some really interesting clues about what's happening if you just think about what you see as the iron starts to emit light. At first, the light tends to be very red and orange. And so once you first start emitting light from the iron, it's a very warm orange-red color. But as you heat the iron up hotter and hotter, what happens is that more and more of the atoms start shaking faster and faster and faster, and so they start emitting some of the other colors, the greens and the blues. And eventually, as you emit all the different colors, what happens, you probably learned in grade school, all the different colors combine and make white. And so as the iron is heated, the atoms are shaking faster and faster and faster. And so some of them are going to be a little bit faster, some of them are going to be a little bit slower, some will be in the middle. But there'll be a range of these atoms vibrating back and forth, emitting all these different colors of light. And eventually you'll have white light, which is all the possible colors of the rainbow. Now, one of the things that this tells us is that it takes more energy to emit some colors than it does other colors. And so as the iron is heating up, the first colors that get emitted are the red and the orange. And by the way, I've written the letters of the main spectrum colors. red, orange, yellow, green, blue, indigo, and violet. Violet's basically purple. But as you first start heating it up, it's the red and the oranges that get emitted first because they get emitted at the lower energies. Then as you introduce more and more heat to the iron, more and more atoms start shaking faster and faster, and that brings in the other colors, the greens and the blues and the violet. And once you have atoms emitting all the different colors, it literally becomes white hot. This is called a continuous spectrum. It's continuous because there are no gaps in it. You got all the possible colors, and when you add them all together, you get white light. The other thing that this example tells us is that the color that you get depends on how fast the charges are being shook back and forth. And so the frequency at which the charge is being shook back and forth, that gives you the color. And this is a very important idea for us. The frequency of a light wave equals its color. And so the frequency at which the thing making the light is shook back and forth, that's going to be the color. And when you look at the wave itself, how many times per second it goes back and forth, the wave goes back and forth, that's also its frequency. And so the frequency corresponds to color. That's a very important concept when you're talking about light. The next thing we want to talk about is what are called electronic transitions, which is the second method by which light can be emitted. So one way to think about an atom is the so-called Bohr model, where you treat the atom as a solar system. Now, atoms aren't really like this, but it's sometimes a useful way of thinking about atoms. And in the Bohr model, we have the nucleus, which is at the center with all the protons and neutrons that are going to be the protons are positively charged. And then we have the electron orbiting around the nucleus like a planet orbits the sun. Now, the electrons are confined to certain regions of space. They can only orbit in certain areas, but not in other areas. And the areas where the electrons are allowed to be are called the electron shells. And so this could be another shell in which an electron could be, and this could be another shell in which an electron could be. The electrons could be in any of these shells, but not in between the shells. So there are only certain parts of space where the electron's allowed to go. And what's interesting is that if this atom absorbs just the right amount of energy, maybe light gets shined on it, maybe it gets bumped, there's something that causes it to absorb some kind of energy. And if it's just the right amount of energy, what will happen is an electron can jump from one shell to another shell. And when I say jump, I actually literally mean teleport. The electron will disappear in one shell and it'll reappear in another. So this electron might absorb some energy and hop into this shell. Now, it's jumped up from the bottom shell up to this other shell. It's going to hang out there for a while. But then what's going to happen is it's going to fall back down. And when it falls back down to where it wants to live, the energy that it gained being promoted into the higher shell, it gives back. It gives it back as light. And the frequency at which the light shines depends on how big the jump is. So different amounts of jumps give you different colors or different frequencies of light. And the spacing between the shells is different for every atom. So a particular jump in one atom will give one color, but in another kind of atom it would give a different color. Now, here's to complicate things. I drew this with 3 shells because I wanted to show you another possibility is that this electron could jump down to this intermediate shell, and that would give off a particular color, and then it could go back to where it wants to be, and that would give off a color. Or, as I said previously, it could jump all the way back, and that would give off yet another color. So there's 3 different possible colors that this scenario, the atom in this scenario could emit. So you don't get every possible color with an electronic transition. And by the way, electronic, literally a transition of electrons from one shell to another. These electronic transitions only give off certain colors of light. And each atom gives off a specific set of colors. It's like a fingerprint. And so by looking at the colors that a specific atom gives off when it undergoes these electronic transitions, you can actually figure out what that atom is. Because it's like identifying a criminal by his or her fingerprint. You can see that the pattern of colors that a particular atom gives off is going to be unique to that atom. And so if I see light coming from an atom and I see a certain set of colors, I can go look up which atom that set of colors belongs to. And the process of identifying an element or a chemical by the colors it gives off is called spectroscopy. And spectroscopy is a technique that's used everywhere in physics and in chemistry. So it's a very, very important way of looking at the world. Basically, spectroscopy means you're analyzing the colors that something is giving off. That means the frequencies of light that it's emitting. And from that, you can deduce certain things about whatever it was that was emitting that light. In this case, we can actually tell what something is made of based on the light that it gives off. That is spectroscopy. Okay, so the tool that is used to do spectroscopy is called a spectroscope. And a spectroscope is an instrument that separates and spreads light into its component frequencies. Or, as you know, that means its component colors. So how do you do that? How do you separate white light into its component colors? Well, it turns out there are actually multiple different ways that you could do that. But there's one way that most people are already familiar with, and that's to use a prism. As you probably know, a prism is just a piece of glass that's shaped kind of in a pyramid, a triangular kind of a shape. If you send white light into a prism, what happens as the light passes through the prism is it separates out into its colors. Now, if you have the light, say, coming from an atom, it won't necessarily be white light because it might not contain all the colors. As we already talked about, atoms only emit certain colors. They don't emit all of them at the same time. And so the light coming from an atom won't be white, but you can still send it through a prism and separate it into whatever colors are in fact there. And as we also talked about the particular set of colors coming from an atom, that's like a fingerprint that you can use to identify the atom from the colors that it gives off. So here's an example of some different gases that have been ignited by a flame, and they are giving off distinct colors. And so you can see the one at the top is strontium, and it has kind of a reddish color. And if you look at all the colors that it gives off some blue and some yellow-green, but it also gives off a lot of orange and red. And so all of these colors combine and make that kind of reddish color that you see there. Potassium, on the other hand, gives off a completely different set of colors. These are all the colors. Now, remember, if this were white light, you would see every possible color of the rainbow up here. But in each of these cases, you're only seeing the specific colors that each gas gives off. And so you have potassium here, and barium, and copper. Copper is very interesting. It doesn't give off that many different colors, and you see a lot of strong greens with a little bit of blue and a little bit of yellow. So it makes for a very green coloration. That's the color that copper tends to give off. And of course, the main idea here is that if I'm looking at the light coming from a gas, I can match it up to whichever one it matches to and use that to identify what gas that is. Because each of these sets of colors is like a fingerprint that identifies that material uniquely. Here we see this process of atomic excitation, which causes what we call electronic transitions. I already went over that, so I'm not going to go over it in detail again, but you can sort of see from the slide here, it gives you those ideas. Okay, so let's check our understanding. The hydrogen spectrum consists of many spectral lines. How can a simple element have so many lines? And the answer is that one electron can be boosted to many different energy levels. And we talked about how as it goes up to a higher level, as it falls down, there are different paths that it can take on the way down, and each one will give off its own particular color. So you can get multiple colors from the different shells that the electron's hopping to and fro from. Another example is when an atom is excited, it's A, electrons are boosted to higher energy levels. Okay, we know that one is true. Atoms are charged with light energy. I don't know what that means, charged with light energy. I don't think that's it. Atoms are made to shake, rattle, and roll. That's a little tongue-in-cheek, I think, but I think we can discount that one. None of the above. Well, we already know that it's A, so that seems to be the only one that's valid here. When an atom is excited, its electrons are boosted into higher energy levels, or those higher shells that we talked about. Now, in the very late 1800s and early 1900s, a German physicist named Max Planck, he hypothesized that when you heat something up and cause it to emit light, the light that comes off, the radiant energy that comes off, it does so in discrete bundles called quanta. And his idea was that each energy bundle was proportional to the frequency of the radiation. Einstein came along and said that light itself is quantized. And a beam of light is not a continuous stream of energy, but it consists of countless small discrete particles, each called a photon, a quantum called a photon. For many years, this was a big debate in the history of science. Does light behave like a wave, or does it behave like a particle? So some people thought that light behaved like a wave, and some people thought it was like a BB shooting across. So the sun emits light. Some people thought it was emitting a bunch of waves. Some people thought it was emitting like something like a bunch of BBs. Those BBs would go in your eyes and be sensed. Those particles. But it turns out that neither of these pictures is exactly right, but each one is partially right. The real answer is that light consists of packets of waves. So what does that mean? Well, instead of a wave that goes on and on forever, it's a wave that has a finite number of pulses. And so if you look at this wave, if you kind of zoom out, it looks more like a particle. You just see, because this packet of waves is traveling, say, to the right, it bumps into something, it's going to feel to that something like a particle bumped into it. But if you zoom in, it looks more like a wave. And so in physics, this was really confusing for a long time because some experiments made light seem like it behaved as a wave, and other experiments made light seem like it behaved as a particle. So there was a big debate for a long time. Which one is the truth? What is light really? Turns out it's both. It's both a particle and a wave. And that little packet of a wave is what we call a photon. And light consists of photons, and the wave inside has a particular frequency, and that corresponds to the color of that photon. And the key idea in this slide is simple. The amount of energy that exists in a photon is proportional to its frequency. In other words, if I double the frequency, I double the energy for every little packet of light. So blue light has little packets that contain about twice the amount of energy that the red packets of light have. Blue photons have about twice as much energy as red photons because blue photons vibrate at about twice the frequency of red photons. That's what it means when we say the energy is proportional to the frequency. Okay, let's check our understanding. Which of these has the greatest amount of energy per photon? Red light, green light, blue light, or do they all have the same amount of energy? And the answer is, of course, C, blue light. We know that red light has the lowest energy. Think about we're heating up our bar of iron. We see the red light first, and as we add other colors, Roy G. Biv, each color requires more energy than the color before it. And so blue light has the highest amount of energy. Now, which of these photons has the smallest energy? Now, this is an interesting question because it brings in something I haven't mentioned yet. What we see as light is only a small part of the electromagnetic spectrum. There's visible light, Roy G. Biv, but you guys also know that beyond the red, there's something called infrared. It's a kind of light that we can't see, not with our eyes anyway. We can build instruments that can detect it, but our eyes can't perceive infrared. On the other side of the violet is a region called ultraviolet. And you guys know the spectrum goes on and on. There's radio waves, there's X-rays, etc. In fact, if we look at the whole spectrum, at one end you have gamma rays, then it transitions to X-rays, ultraviolet, the visible. Now, if this is the ultraviolet side, that means we start with the indigo, violet, blue, and on the other end we have red, and then beyond the red we have infrared and radio. And so these are all the parts of the spectrum. And remember, higher energy goes this way. It goes towards the blue. And so X-rays have a higher energy than visible. Visible has a higher energy than infrared. And so which of these has the smallest energy? Well, you tell me. Look at the chart, pause the video, and you answer the question. Which of these photons has the smallest energy? I'll wait. Pause the video, answer it, please. Okay, hopefully you all paused the video and thought it out. So clearly of the ones listed here, infrared has the smallest energy. So the answer was A. The next topic we're going to talk about is the so-called quantum hypothesis that was proposed by the Danish physicist Niels Bohr. And he explained how these atomic spectra form, and it's basically just what we said. The electrons get promoted into higher energy states, and they jump to a higher shell, and when they fall back, they emit light. Now, what Bohr said was that the potential energy that the electron has depends on its distance from the nucleus. And so if it jumps to a higher shell, it's farther away from the nucleus and it has more potential energy. And when an atom absorbs a photon of light, it absorbs the energy. That's one of the ways that we can cause these electronic transitions. And so what happens is the low potential energy electron, that is the electron in a lower shell with a lower potential energy, gets boosted to a higher shell, and because it's further away from the nucleus, it has a higher potential energy. And that's the potential energy, that's the energy that's stored in the atom that when the electron falls back down, it can give back as the form of light. So in this next slide, we'll talk about this idea a little bit more. When an electron drops down closer to the nucleus, it emits a photon of light. Now, Bohr reasoned that there must be a number of distinct energy levels within the atom. Each energy level has what we call a principal quantum number n. And key idea here, n is always an integer. 2, 17, 4, 3, but not 3.14, not 6.82. It has to be a whole number, an integer. And the lowest energy level corresponds to n equal to 1. That's its quantum number. And that's the energy level where the electron is closest to the nucleus. It's not allowed to get any closer to the nucleus than that. So, testing our understanding, which of the following numbers could possibly be a quantum number? Well, obviously it has to be C2, because all of these are fractions, and you can't make a quantum number be a fraction. It has to be a whole number, an integer. One of the benefits of Bohr's quantum hypothesis is that it explains why atoms don't collapse. Well, why would they collapse in the first place? Well, remember, if an electron is moving back and forth, it's supposed to emit light. That was our method one for light to be emitted. I have a charge and I shake it back and forth. If I have it going in a circle, that's like shaking back and forth, right? So the electrons spinning around the nuclei, we would expect them to emit light, but that light would have to come from somewhere. And so what we would expect is the electrons, as they emitted light, they would lose energy and spiral into the nucleus. Obviously, that doesn't happen because matter doesn't spontaneously self-destruct. So Bohr wanted to come up with, some way of understanding why that happens. And what Bohr said was that if the electron is bound to an atom, that rule that vibrating or accelerating charges emit light doesn't apply. Instead, electrons can only lose specific amounts of energy when they make transitions to lower energy levels. And when an atom reaches the lowest energy level, which is called the ground state, the electron cannot lose any more energy than that, and it can't move any closer to the nucleus. That's why electrons don't spiral into the nucleus and atoms don't disintegrate or blow up or whatever. Before I go into the content of this slide, I want to mention the name of a physicist who's a very famous physicist, but his name is almost always mispronounced. So he was a French physicist, so his first name, a lot of Americans would read that as Louis, but in France it's pronounced Louis. So Louis de Broglie is how you actually pronounce this name. I've heard it pronounced de Broglie, de Broglie, de Broglie. It's actually just Louis de Broglie. That's how you say the gentleman's name. And Dr. de Broglie made a very, very interesting hypothesis back about 100 years or so ago. He posited, for many, many years, there was a debate as to whether light was a particle or a wave. And as we already talked about, we know that the answer was it's both. It's something that can be either a particle or a wave, depending on what experiment you're doing. It's something that has aspects of both. What Dr. de Broglie posited was that electrons and physical matter can behave the same way. In other words, we tend to think of electrons as particles, but he suggested that you could also think of an electron as a wave. And it turns out he was right. Electrons, like photons, are things that exist in a state that has wave-like properties as well as particle-like properties. And so an electron in some experiments will behave like a particle, and in other experiments it'll behave like a wave. And he actually used this idea to kind of explain why electrons form shells. Imagine you have a wave, and so a wave is going to go on and on. It's going to rise and fall like this. And imagine instead of it going in a straight line, imagine you took that wave and you wrapped it around a circle. And that's what we see here in the picture below. And so I want to look at this one that is kind of shaded green. If I start here at the top and I go tracing that wave, what I see is I keep going around the wave. As I keep going around the wave, eventually I get back to where I started, and it makes a closed loop. If the wave was a little bit too long, then it wouldn't come exactly back together at exactly the same place. It would not reinforce itself, but it would just kind of jumble up. But if I have it at exactly the right length, it's going to completely close in on itself. And this is something that's called a standing wave. And so the idea was that for a wave, if the electron is behaving like a wave, it's only going to fit in the orbit that corresponds to its wavelength, the one that makes it match up. And so it was a very intriguing idea, and in the early days of the study of quantum physics, it was something that really helped convince people of this idea that electrons were confined to specific shells. Of course, now we have tons of evidence that this is true. We know it's true, but this was a very interesting idea that Dr. de Broglie posited back in the day. Now, here we see kind of a visual representation of all the different shells of a particular atom, and they don't all actually look spherical in this way, but this is, a useful way to think about it in a very simplistic fashion. And you can see some numbers here. These numbers give you the number of electrons that each shell can hold. So the first shell can only hold 2 electrons, the second shell can hold 8, the third one can hold 8, the next 2 can hold 18, the 2 after that can hold 32. And so as you start filling the shells up, I've got 1 electron, 2 electrons, the next electron up will go into the second shell. And so the next 7 electrons to make a total of 8 will fill that second shell. Then if you add another electron, it'll go to the next shell, and so on. And remember, the electrons are only allowed to live in the different shells. What's interesting about this idea about shells is that it explains a lot about the periodic table. How so? In terms of chemistry and how things behave chemically, what really matters is how many electrons there are in the outermost shell. And so if we look at the first period, we can see hydrogen has 1 electron and 1 proton. Helium actually will have 2 protons and 2 electrons. And so as we increase the atomic number, what we find is, remember, the innermost shell can only have 2 electrons and it's full. And so if you add a third electron, it goes to the next shell. Well, hydrogen has 1 electron here. That's the outermost shell. That's the one that's involved in chemistry. Here, the inner shell is completely filled. The outer shell has 1 electron. That's what's involved in chemistry. So that's why hydrogen and lithium are chemically similar to one another. They both have only 1 electron in their outermost shell. Now, as I go across the period, I've got 2 electrons in the outermost shell, 3 electrons in the outermost shell, all the way up to 8. And remember, 8 is the most electrons that can fit in the second shell. Once you have completely filled the shell, you go back, you created the next shell, and you go back to having a single electron in the outermost shell. So sodium is chemically similar to lithium and hydrogen. These all behave similar ways chemically. And so that's because they each have 1 electron in the outermost shell. And we also see why the pattern, because once you get the shell is completely filled, then you go back to having 1 extra electron, 2 extra electrons, and so on. And so this explains why you have both the groups with similar chemical properties, and you have the periods which show the same trends because they each have the same pattern of how many extra electrons are in that outermost chemical shell. And so that explains the structure of the periodic table. And chemists, of course, can use this. Looking at the periodic table, they can understand a lot about how a particular element is going to behave in a chemical reaction. Now, hopefully, all of that made sense. If you have any questions, please do not hesitate to contact me. I would be happy to help you further if I can. So now that you've gone through the PowerPoint and you have hopefully read the chapter, you should be ready to tackle the homework. So good luck with that, and I will see you guys when we get back to the next chapter.